Welcome. This is Dr. Morton, and this is the video for Chapter 9. I think you're going to find this interesting. I want to say at the beginning that I'm going to cover information that essentially relates to two separate courses that I teach after logic design. So for the electrical engineers and the computer engineers, you'll both have to take microprocessors 1. And for the computer engineers, you'll also have to take digital systems design. Well, we cover the hardware description language, Verilog, in digital systems design, and we show how to write code and use microprocessors or microprocessors to do things in Micro 1. Both courses have labs. So what I'm going to cover is essentially 2 semesters worth, and I'm going to try and do it in 40 minutes or less. So needless to say, we're going to be kind of going over the surface. We're not going to be taking a deep dive. The purpose of this is to give you the 10,000-foot view of hardware description languages and to be able to compare that to what microprocessors do. And let me just say right off the top that as time goes on, we're already seeing the merging of what we can do with a microprocessor into what we do with programmable hardware, and in fact, what we also see is that many microprocessors have now incorporated some built-in programmable hardware, and many programmable hardware chips have incorporated microprocessors. So it makes sense that these two worlds are colliding because the programmable hardware world can do some things so much faster and better than a microprocessor, but microprocessor can do some things so much better and more efficiently than programmable hardware. So because of that, we're going to really we need to understand both. And obviously, microprocessors are made out of the same types of hardware that our programmable hardware is. So they're really not that different. Okay, having said that, let's get going. Okay, so the chapter picture for this chapter basically shows a bunch of combinational devices, but it doesn't show the actual devices like we did in the last chapter. What it shows is how we represent these in hardware description language. Okay, so we're going to talk about muxes first, and then we'll talk about some other things. But before we dive into this, I do want to talk a little bit about hardware description language. So hardware description language, before I do that, let me go over the learning objectives. So I want you to be able to describe 3 major advantages of using hardware description languages for design. I want you to be able to write a simple combinational module in Verilog, and I want you to explain 3 different implications for when we have a microprocessor-based solution versus when we have a Verilog field programmable gate array-based solution. Now, I haven't really defined what FPGAs are yet. So if we click on this, what we can see is that FPGA stands for Field Programmable Gate Arrays. It's a very large integrated circuit that generally has hundreds of input and output pins and a large number of generic logic units. These logic units can be programmed to become a very large range of different hardware configurations. It's programmed using a hardware description language like Verilog, with an integrated development environment, and we use Vivado for the FPGA chips that they manufacture. And this hardware description and this hardware development this integrated development environment creates a bit file from our hardware description language code, which we can write in several different hardware description languages, but the one that we teach in this department is Verilog. The others are named VHDL, System C, System Verilog, and some others. But currently, probably Verilog is still probably the most used one, although System C and System Verilog are moving in to sort of take over eventually. This bit file then is loaded into the FPGA's programmable memory, and it flips switches, hundreds of millions of switches that basically configure, that change how this how this programmable hardware is connected up to make whatever device you designed. All right. And interestingly, these large chips, you can actually put a microprocessor on them by putting on that bit file or incorporating a microprocessor bit file into your larger bit file. All right. Why do we use these language-based descriptions called hardware description languages for making hardware? Or maybe another question is, why do we use computer languages for programming computers? Well, the reason we do this is because it's much easier to write, to develop the logic and hardware we're trying to create using English language statements than it is to create a large schematic of a circuit. I've already given you the example of the NVIDIA chip for the schematic. If we used 1 square inch for each transistor, the 14 billion transistors would result in a schematic of, I forget what the number was, but more than 10 square miles, which is crazy. I mean, that's just, impossible. You can't, there is no paper that big. There's no area to roll it out. There's no ability for even a team of humans to draw 14 billion transistors. It would take them multiple lifetimes to even get close, and all the mistakes they would make. And then once you had that schematic all drawn out, how could you even use it? You couldn't transport it to another group of engineers and have them implement it because it's too big, and where would they roll it out? So it's ridiculous. So the only way to do this is to use our tools to deal with complexity, which is we have hierarchy, we have levels of abstraction, we have regularity and modularity. And what you do is you create submodules, and then you kind of hide those, and you add those all up, and eventually you can come up with very complicated things. Now in that NVIDIA chip, there's lots of replicated sections because a lot of it works in parallel. But so once you create one of those modules, you might replicate it thousands of times in creating this chip. All right, well, so that's one of the things that's driven, and the other thing that's driven us towards using these English language-based statements is that we can reuse designs that we've done in the past. So, for instance, 10 years ago, you might have written a really great set of hardware to, say, be a high-speed adder. Well, you wouldn't necessarily want your chip to be made with the same technology as the one done, say, 10 years ago, but your code could be now put into today's integrated development environment, say for making integrated circuits, and it could crank out all the photomask and everything to make that integrated circuit with a feature size closer to, say, the 10 nanometer cutting edge standard that we're sort of at, as opposed to maybe 10 or 15 years ago we were using 150 nanometer features, or maybe even 300 nanometer features. So the code could be the same, and all we did was change the synthesizer in the integrated development environment, and it updates our code. So that's another real advantage: the ability to use old designs to build on the shoulders of previous designs, and to be able to manage the complexity of very complicated chips, all using these English language statements in Verilog with our fancy integrated development environments that have synthesizers. Okay, that's enough. I don't. Obviously, we could talk about this for a very long time because there's a lot to it, but I don't want to do any more. Let's look at some examples. Well, first off, a little history. HDLs came to existence in the early 1980s, both Verilog and VHDL. initially they were just used to document the hardware that was made and to document how it was put together and what it was supposed to do. And then later on, they realized they could use this documentation language to actually do some simulation work, which they really wanted to do. And then finally, they began to write these crazy synthesizers that could actually turn these statements into bit files for programmable logic, or actually all the photomasking steps to make the integrated circuit in a foundry. And so that's what we've got. And there's on the integrated circuit side, there's some things like Cadence, for instance, is a very large program, and that's what a lot of people use to make integrated circuits. There's some competitors out there. Mentor Graphics, I think, is one, and there are several others, I think. Only a handful, though, of really big ones that can do almost anything. And the people at Intel, they write Verilog code to describe their next processor. The people at AMD do the same thing. And these very fancy processors are just big Verilog files. ARM, that's responsible for the vast majority of cores in the world today, they don't make any actual chips. All they do is write hardware description language files. And then you license their file and integrate your additions to that file, and then you manufacture a chip and sell it. All right. And that's what a lot of people do. There's still a few microprocessor companies out there making their own cores, but even those are also making ARM cores as part of their line. Okay, let's look at how we would do a MUX in VHDL. So let's do this. There are several different ways we can do this. Okay, well, here's a simple circuit in using gates. We have A and B going into an AND gate, and then the output of that we're calling C, and then we have a separate variable D that's going into this OR gate and outputting E. So let's see what this would look like. So in VHDL and Verilog, I wrote it out both ways. These are basic, we call these basic assignment circuits. In VHDL, and this is, I'm not going to show you a lot of VHDL, but I'll throw this in here. You can see we have C is assigned the signal A ANDed with the signal B after 5 nanoseconds. So notice we do put in some timing information. And we use that timing information when we simulate this circuit in our hardware, in our integrated development environment, simulating our hardware description language to see if we're going to have timing problems. And this is really very important, and it really helps us minimize problems. Sorry, I didn't need to do that. And then we have E is assigned the results of C ORed with D after 5 nanoseconds. So you can see from a change in A, 5 nanoseconds here, 5 nanoseconds there before we would see it reflected in the output. Verilog, and notice our operators are actual, we write out AND, we write out OR, and then we have the timing thing after. And notice we have this funny equal sign, the arrow and the equal sign. In Verilog, we have a slightly different syntax. We usually use the assign keyword, although it is optional. In fact, Verilog is very permissive. VHDL is very strict. You have to get the syntax exactly right in VHDL. In Verilog, you can slop it around and leave out all sorts of stuff, and it'll still do its best to make sense out of it. That's probably why Verilog has become most popular in the United States and VHDL in Europe. All right, so C, and then this #5. This is an inertial delay or a propagation delay, just like this 5 nanoseconds. And we have to have a statement at the beginning of the program that says it's going to be in nanoseconds, which it almost always is. So C is assigned after 5 nanoseconds the result of A ANDed with B. Now note we use the ampersand here. It's the same syntax as the C language for the most part, with a few exceptions. And the single ampersand is a bitwise assignment operator, and the double ampersand is a logical operator. Same with the bar. The vertical bar is the OR operator, and the single vertical bar is the bitwise OR operator, whereas the double bar is the logical OR operator. Now I'm gonna shift this 1 minute, and what I want to do is I'm gonna just illustrate that a little bit before we go too much further. So let me do that. Okay, so bitwise and logic. So for bitwise, in Verilog, we use the ampersand for and we use the double ampersand for the logic. We use the vertical bar for or, and we use two of them for the logical or. And then there is no logical exclusive or, so we just use that. And the bitwise invert is a tilde, and the bitwise invert, the logical invert, is the exclamation point. Now, what's the difference between bitwise and logical? Well, in bitwise, if you just have single bits, there's no difference. But if you have vectors, which are multiple bits, then there's a big difference. This takes each bit separately, and this takes all bits together. Now, the big difference is we use this concept of true or false. So in the logical world, any non-zero equals true, and we represent that with 1. And 0 equals false, we represent that with 0. Whereas in the bitwise, it's each bit by itself compared to another bit. Okay, so supposing we have two variables, and we have a funny way of writing variables in hardware description language. So let's say we define A, it equals, we're going to say it's 4 bits, so we write 4 apostrophe or tick, 4 tick, and we can use binary, we can also use hex or decimal. I think we can even use octal, but we're going to avoid that in this course because it doesn't really have much use anymore. So A equals 4, and there's some other things you can use too actually, but A equals 4 tick B, and then we put in the digits. Let's say we're going to do 1 0 1 0. That's going to be the value for A, and let's say B is going to equal 4 tick binary, and it's going to be 1 1 0 0. And let's say we're going to define C equals 4 tick, and we'll do a hex, and let's do this, and we'll make this 5, hex 5, which actually would be equal to 4 tick B 0 1 0 1. Okay, just so you can compare. All right, so if we do, and then we'll take D as another 4-bit vector. So we'll say D equals, let's do A logically ORed with B. Well, is A completely 0? No, it's not 0. So A reduces to a logical true. Is B 0? No, B is not 0 either. So it reduces to a logical true. So true, logically ORed with true, equals true. And we always represent true with, in this case, 4 tick B 0 0 0 1, since it's a 4-bit vector. All right. So when you're all said and done, D equals A logically OR with B is going to be equal to 0 0 0 1. What if we took D equals A bitwise ORed with B. Now we have to compare all the bits, see what we get. So we compare this with this. Well, 1 and 1 are always a 1. A 1 and a 0 is a 1. A 0 and a 1 is a 1. And a 0 and a 0 is a 0. So that's what we get for B. And of course we would write that 4 tick B 1110. Okay, so that's if you logically. What if we bitwise ANDed it? So let's do D equals A bitwise ANDed with B. Well, so if we do the bitwise AND, the first bit, 1 and 1 is a 1, 1 and 0 is a 0, 0 and 1 is a 0, and 0 and 0 is a 0. So this would be 1, 0, 0, 0. So you see how that works. But if we do the logical, then you just evaluate whether it's non-zero or 0. And if it's non-zero, it's true. If it's 0, it's false. And then you're comparing true and true is true. True and false would be false. And in the ANDing, false and true would be false. Okay, but in ORing, false and true would still be true. That's a logical OR. Okay, let's do the bitwise invert. If we say if we say D equals the bitwise invert of A, what's that going to be? Well, we're going to take all the bits in A, 1, 0, 1, 0, and we're going to flip them 0, 1, 0, 1. So that would equal 0, 1, 0, 1. What if we did the logical OR? D equals the logical OR of A. That's just going to equal 0 because A is non-zero, so it's true. The logical inverse of true is false. So that's, and since D is a 4-bit vector, you get 4 zeros. All right, so that hopefully shows you. Okay, now we're going to talk about how to do the MUX. So there are actually a number of different ways to do the MUX. So we'll show you some different ways. So this is one way. Let's see, let me move this over a little bit. So here's one way to do it. We have, this is how you write a Verilog module. You always start with the keyword module, then you give the module a name, and then you list the variables that are going to appear to other modules or the outside world or connect the pins on the chip or whatever. There can be internal signals, and actually, let me pause this a second. Yeah. Okay, so here's what the module looks like. I had a little error I had to fix there. Okay, so we call it keyword module name MUX4, and then we have 4 variables, I, A, B, and F. Now here in this list all the variables that are going to appear to the outside world, but we then describe them a little better. In this case, we call it input A and B, input I, that's a vector 3 down to 0. It's a little confusing, and output F. We write this backwards just because that's the correct hierarchy. When we write bits, we write the higher order bit first, and then the next, and then the next, and then the next. So this is this is I3, and this is I0, and that's 1 and 2. So 0, 1, 2, 3. But note, we write them 0, 1. We write them 3, 2, 1, 0. So that's why we do 3 to 0 when we define these bits. You can write it the other way. It's just backwards from what we're actually going to use. So that's why we write it this way. And then the output F. Notice input, and output. This tells us which way these variables are moving. And there's also an in-out. Then here's our assignment statement. This could be all on one line, but it wouldn't fit in the box very well. And so if you look at this, we're using the logical operators for the logical inverts and the bitwise, which is probably wrong. We probably should use the logical, all logical or all bitwise. But anyway, that's what I did. For a single bit, it doesn't matter. And A, B, and each of these individual bits are just single bits. So I0 is an individual bit, I1 is an individual bit, I2 and I3 and A and B, of course, are. So here's the way it works. F equals, well, let me write it out on the paper, and it'll maybe be a little more obvious. So remember, A and B are our, these are our selection lines. Sometimes we'll call these cell A, and cell B, but I just used a little shorthand there. All right, so F equals A prime, B prime, I0, or A prime, B, I1, or A, B prime, I2, or A, B, I3. So notice A prime, B prime, A prime, B, AB prime, and AB. So those are the four possibilities, and that selects for I0 when they're both 0, I1 when it's 0, 1, I2 when it's 1, 0, and I3 when it's 1, 1. Now, we can also do we also can do this two other ways. And we can write it like this. We can use this special assign statement, which is valid in C, but you may not have used it and you may not have seen it. And it's this question colon construct. And we've actually nested another question colon construct in here, and another question mark colon construct in here. Let me just explain it. So you have a variable, and this equates to logical true or false. And then if it equates to logical true, we take this, we put a question mark after it, we take this, and if it equates to false, we take this. Now in this, we have another logical variable, b, and if it equates to true, then we take this, and if it equates to false, we take this. And here we do it again, b, if it's true, I1, and false here. So pretend that we have A is 0 and B is 0. So what would we get? Well, if A is 0, we get this answer. If B is 0, we get this answer, which is I0. So A0, B0 makes F equal to I0. What about A1, B0? Well, that should be 2, right? Well, if A is 1, we're going to take this one. And if B is 0, we're going to take this one. Oh, look, it's I2. So it works correctly. And then finally, we can also write it like this. Now this is, I call this a bastardized way to write it, because we're using this always block, which I'm not going to introduce until the next time, the last third of the course. And this always block is supposed to be used primarily for sequential designs, where we're controlled by a clock. But Verilog allows you to misuse it for combinational design. And the synthesizer is smart enough to realize that it didn't really mean to use it for, that it didn't really mean it, that we were just kidding, and it's going to resolve it back to a combinational design, even though we're using a sequential design construct. Again, Verilog is very permissive. VHDL is not. It doesn't let you do this. But people like to use this because they can use these if statements. If statements are not legal outside of always blocks. So that's why people do this. Okay. All right, I think that sort of makes sense. And I'm not going to explain the always block until we get to it later on. But there are several different ways to do this. Oh, and the execution time for this is 10 nanoseconds. And depending on, assuming it's written as an assignment statement like these are, and this is, then anytime A, B, or any of the I's change, F will be recalculated. And that'll be recalculated in 10 nanoseconds. It may not change, but if it does, it'll change in 10 nanoseconds. But anytime A, B, or any of the I's change, it will be recalculated. And this is this is because these English language statements here result in actual hardware. Okay, so what I want to do now, I want to sort of talk about how we might actually, using that code, also write this in a C language statement. And so if we scroll up here in the book, you'll see this is what it looks like if we write it in C language. We use an infinite while loop, and we use these if statements. Now in our computer language, we can use our if statements wherever we want. But in Verilog, we can only use them in always blocks. And that's why we had to use those assignment statements, or that question mark colon construct in assignment statements. But if we use the always block, then we could use the if statements there, and it would look very similar to this. Okay. Now notice this has an execution time of about 6 microseconds. That's compared to the 6 nanoseconds that we are. Yeah, I guess it was about 6. Maybe it was about 6 nanoseconds, or maybe a little bit more than that. What did we actually say? 20 nanoseconds. So it's about 300 times faster. About 300 times faster if we do it with an FPGA versus a microprocessor. And that is given that the microprocessor is only executing this infinite while loop. If we have it doing other tasks and every now and then coming back and doing this, it's going to take a lot longer. It might take minutes instead of nanoseconds. But if you're just staying in this tight loop, then it would be about 6 microseconds, depending on the processor speed. But we're saying run it at 32 megahertz. Whereas this FPGA can run at 200. It's not really running at a speed. It is, because it's hardware, it's going to execute as fast as these gates can change. Now the FPGAs do have clocks because we actually make state machines on them, and those run at about 200 megahertz typically. Okay, so what is the big difference between a MUX implemented on this FPGA, which is programmable hardware using a Verilog hardware description language generated bit file, okay, versus a C language program stored in a microprocessor? And the answer is the FPGA is about 300 times faster, because it's always ready to, and it's always ready to execute, whereas we'd have to dedicate the whole microprocessor just to doing this, or maybe use something called interrupts, which you may not have gotten to yet. We'll talk about that in Micro 1. All right, so even though they can do the same thing, there are constraints. Now notice here we have 325 pins, and we let this multiplexer be connected to these pins, and we use pins A0, 1, 2, and 3 for I0, 1, 2, 3. We used the output F we had connected to PTA4, and I did switch that around. Let's see, I think I actually showed that. Yeah, I cleaned this picture up a little bit. So you notice 0, 1, 2, 3 are our inputs, IN. We have an output F that's connected to PTA4, and then our 2 select lines, which are also inputs, go into PTA 5 and 6. Now that's just how you would arbitrarily connect it. And again, 20 nanoseconds roughly runtime. If we implement this on a microprocessor, then you have something like this, where we have maybe 80 pins or less, and we have the inputs, we'll say PTA 0, 1, 2, 3, the outputs PTA 4, and the selects, the A and B, are PTA 5 and 6. And so what I want you to see here is that this would take up quite a few pins on this microprocessor, but if you had 80 pins, you'd still have things left over. Normally this would be it's kind of a contrived comparison, because you probably wouldn't ever use a microprocessor to just do a multiplexer, but you could. It will do it, and I'm trying to point out kind of the differences. Okay. All right. So so I wanted to move on. I want to talk a little bit about, in the book I list the rules for identifiers. So they're in Verilog, and also in C, they're very similar. But in Verilog, they're case sensitive usually. They can include the letters, numbers, and the underscore and the dollar sign. They have to begin with a letter or an underscore. They can't begin with a number or a dollar sign. They can be up to 1,000 characters. Can't have any spaces, and they can't be any of the reserved keywords like assign, module, always, things like that. Constants, on the other hand, and I already showed you this, are very, very complicated, especially if you leave out parts. But remember, we normally write them, and let me just go back to the paper. We normally do n tick, and then we have a base here, and then we have our actual digits. So the n is the number of binary bits. So let's say if you wanted to do 2 hex digits, then you would do 8 tick H, and then you could do, say, A6. And that would be A6 in hex. 4 bits for A, 4 bits for 6, and that gives you your 8 bits, and the H means hex. Or if you wrote it out in binary, 8 tick B 10100110. And that would be A6 in binary. Okay, and you remember you divide these up 1, 2, 3, 4, 1, 2, 3, 4. That's A, and that's 6. All right. Okay. So we also have operators. Okay, and we've already talked about these. Our bitwise operators and our logical operators. So our bitwise are and, or, not, exclusive or, and exclusive nor. Remember the exclusive or and nor. I didn't talk about the exclusive nor, but it's just a tilde and caret or caret tilde. So it's just the little unary inverter. There is no logical exclusive or exclusive nor. On our logical side, we have and, or, not, and equality and inequality. Notice for the not, we use the exclamation point, and double ampersand, or double bar, and equality double equal. That's really important to remember that in C, and it's also really important to remember in Verilog, because you'll probably get errors in Verilog. But in C, you won't get errors. It'll take it, but it'll actually do an assignment, as opposed to doing just the comparison. And then inequality, A not equal to B. And we use the logical invert there. All right, we have shift operators and rotate operators and concatenation operators. I'm not going to really talk about these much. They're also present in C, and you can kind of look. There are some that are slightly different. The arithmetics are 3 less thans or 3 greater thans. 3 greater thans or 3 less thans. The logical the logical are 2. And then concatenation is just you have brackets, braces, and within the braces you have you separate the things you're concatenating with commas. So if A and B are 4-bit vectors, A comma B in these braces then gives you an 8-bit vector with the A starting and then the B. Okay. Conditional operators. That's the thing we looked at. That's the question colon construct. Very powerful. It's good to know, and it's also totally valid in C. And then we have these relational operators: greater than, less than or equal, greater than or equal, or greater than or equal, less than or equal. And then we have some arithmetic things. I'm not going to say a lot about the math right now because it is complicated, but we have various types of variables, and I didn't really go into this, but we have wires and we have registers. We also have bit variables. We have vectors, which are multiple bits, and then we have integers. Integers are special, and they're differentiated from the bits because you can do multiplication and you can do exponentiation and modulus on integers, but you can't do it. You can't do that on on bit vectors. On bits, all you can do is add and subtract. And usually you're using vectors when you do that, like 4 bits or 8 bits or whatever. Integers are automatically 32 bits. But again, they're not, you could make a 32-bit vector, but that wouldn't make it an integer. You have to call it an integer. All right, I'm not going to say anything else about that. It's just more than we need to cover. And then I gave you some examples in the book where we used logical operators, where we used bitwise operator here and here, and to show you the difference. And there were some checks for you to do. Also showed you how the shift and concatenation operators work, so you can review all that in the book. So what's really the big difference between Verilog and C? Well, the big difference is that there's some slight syntactic differences, but the main difference is in Verilog, when you write a statement, if it's an assigned statement, it will execute anytime the right-hand side variable changes. Whereas in C, you actually have, the processor has to get to that line in the code and execute it. But that's not true. When you make hardware, that hardware is running all the time. So anytime, it's just like having a gate. When anything changes on the inputs to the gate, then the output will eventually, in a small propagation delay time of a few nanoseconds, reflect that change. Okay, 4-bit adder. So I do want to cover this very briefly, and this is going to finish it up. We're already at 41 minutes, so I don't want to take much time. So there are 2 modules here. This is the first module, and it's add4, and it instantiates this second module. You cannot define a module within a module, just like in C, you can't define a function inside a function. But you use functions inside other functions. Same exact concept here. So we define this module and we define this module. This module is a single bit adder. Adds 1 bit of A to 1 bit of B, gives and 1 bit of carry in, and it gives you 1 bit of sum and 1 bit of carry out. All right. So that's how this works. And if you look, we've actually instantiated 4 copies of this add1. So this add4 module is really made up of some variables that appear to the outside world. Just like here, these variables also appear to the outside world. And in this case, there aren't any internal variables. So we have 1 bit of X, 1 bit of Y, a carry in, a carry out, and a sum. Up here, we called our 2 things we're going to add, A and B. We have a carry in and a carry out, and a sum. We gave them different names than ones down here, but it doesn't really matter because there's no collision. These are separate modules. When we instantiate these modules, we have to follow positionally exactly the same order that we define down here when we instantiate them here. So notice, right here I put in add1. Well, that's the module I defined there. That was its name, add1. I have to give it an instantiation number. That's just required, and it has to be unique and different. So I called this instantiation N1, N2, N3, and N4. Could have called it 1, 2, 3, 4. Could have called it X, Y, Z, W, whatever. It just has to be unique, and it has to be there. And then in the parentheses, I populate all of my variables in my port, which are 5-bit variables: X, Y, carry in, carry out, and S. Up here, though, A is 4 bits, B is 4 bits, sum is 4 bits, and carry in and carry out are single bits. All right. And you can see 3 to 0, A and B, 3 to 0, sum. These are inputs, these are outputs. All right. Now notice, in the first instantiation, I'm adding A0 to B0. In the second one, I'm adding A1 to B1, A2 to B2, and A3 to B3. But I'm adding carry in, and I'm getting a carry out of C1 and a sum 0. Notice here, I'm adding in the carry 1, and I'm getting out a carry 2. Here I'm adding in a carry 2, getting out a carry 3. Here I'm adding in a carry 3, and I'm getting out the C out. So the C out is the final carry out. The C in is the initial carry in. And so each of these instantiations is basically passing the carry from one to the next. But notice the order does not matter. You can put this in any order you want. I just put it in the logical order, but it doesn't have to be that way because they're all executing simultaneously. But the final carry won't be available to this instantiation until it's rippled through all these others, and that's why the ripple carry adder takes more time. Okay, notice we have C1, 2, and 3. These are internal signals, not in the port list of A, B, carry in, carry out, and sum. Only the signals in the port list are available to the outside world to be connected to pins or to be used in other modules. The internal signals are hidden away, and that's part of our hierarchy and our levels of abstraction. We want to hide these internal details so we don't have to think about them, and then we could instantiate this 4-bit adder wherever we wanted. Now, I want to show you one more interesting thing, and we're going to quit. And here are the equations for the 1-bit adder. Exclusive OR, X, Y, and carry in is the sum, and you have this construct, and they're all bitwise for the carry out. It's X bitwise ANDed with Y, that ORed with the carry in ANDed with X exclusive ORed with Y. And those are the formulas. And remember I said the formulas for 1-bit adder for the sum and the carry out are complicated. And you can see these are complicated. They weren't simple. All right. Here's what I wanted to show you. You could just write, instead of all that stuff we did above, we could redo this add 4 module, and we could do it just like this. We could say assign the concatenated result of cout, comma, and sum equals A plus B plus carry in. Done. And we can let the Verilog synthesizer decide how to actually implement this with gates, and we don't even have to tell it. And in fact, one of the advantages is it might even use a faster adder logic. It might use a carry ripple adder, or a carry propagate, or a carry look ahead, and it wouldn't use a carry ripple. All right, so I think with that I'm going to quit. I guess I did want to show you. So here's our Verilog code. E equals A ANDed with B, F equals C ORed with D, G equals E ANDed with F. And that's what the hardware would look like. This is what the synthesizer actually makes, either in the form of a bit file to program this circuit into an FPGA, or a bunch of photo masks and steps in the foundry to actually make this on an integrated circuit. And it would probably use NAND gates for all these. It would convert it to NAND form. So it would do all sorts of things. You wouldn't necessarily recognize it. It wouldn't look like this, because the synthesizer is very, very powerful and kind of does what it wants. Okay, I think with that I'm going to stop. Hopefully this is a good introduction, but you need to read through the book, and we're going to talk about it some more in class and in other videos.